Great. I will introduce our next speaker. David is a coding architect at Squer, a VNS software company which is working with different stacks and environments, but always an overarching mission. Connect ideas and provide impact with technology. Please don't forget to submit your question on Slido, and please help me with a warm welcome with David Leitner.
Thanks a lot. Hello, everyone. It's great to be here. Great to be back in front of people. It's really amazing. Yeah. Cool. So first things first, as already mentioned, my name is David Leitner. I will talk about the rise of reactive microservices today. So who am I? I'm from Vienna. I call myself a coding architect. What I basically do in my day-to-day business is I help companies, startups, scale-ups in, building architectures that help the organization to scale. That's how I would describe it. But always very close to the teams. Yeah. And the big advantage for you here today is that I don't have a product, so I don't even do kind of books or stuff like this. So there's nothing I can sell you today. So the guys just asked me if I can come over and can I share a little bit of knowledge or of our experiences with building microservices. And that's basically the thing which I will do here now in the next 45 minutes. Let's see if I can make it. But it's about the rise of reactive microservices. So I assume that everybody knows about microservices, right? Everybody is familiar with the term microservices, the architectural style microservices. Who uses microservices? Can you raise your hands? Who runs them in production? Cool, quite a high majority. Who regrets to run them in production? Yeah, liars. Okay, how about reactivity? That's the second buzzword in this title. Who knows about reactive? Who knows the reactive manifest, for example? Oh, quite a few only. Who does reactive programming on a regular basis? Also quite a few. Okay, that's good. That's what I expected. So we will try to decompose this whole topic to get a little bit all us on the same level when it comes to reactivity, and then we'll deeply dive into reactive microservices. So reactivity is basically the idea of programming or designing upon asynchronous data streams. That's what we try to achieve when we do reactive programming. And the interesting part, and that's for me always very interesting and surprising, is if I go to clients or if I work with teams, the term streams is often very unclear, right? It's like this super hype-driven buzzword where we do all and everybody uses Kafka and stuff like this. But often if I talk to people, it seems to be a very complex term, but that's not the case, right? Stream is actually very simple to describe, right? Anybody has a good definition of how he would describe a stream to his grandma or to his small kid? Simple, right? Everything is a stream. No, just kidding. I teach at university a lot, and that I have students which are quite unmature, which are quite junior, which dive into our industry. And I always explain streams very simply, and I found out that also helps more senior engineers actually to kind of untangle this complexity around streams, which is definitely not there, right? If you think of programming, of data structures in programming in a very simplified way, then you actually end up with two axes, right? You have on the one side space, and on the other side you have time. So the axis of time and the axis of space. And this looks now very complex, but isn't. But if you stay in singular space and if you stay in synchronous time, then we have something which we tend to call a value, right? No big surprise, and the value has a get and a setter. But if we move from singular space to plural space, then we have something which we tend to call a collection, and the collection usually has an iterator and has a generator. That's super clear, right? Each programming language supports these data objects or these data types out of the box. If you now move from synchronous time to asynchronous time, right, then we tend to have something which we call a promise in singular space. So a promise usually has a deferred and a resolver, and the interesting part is many programming languages, many ecosystems out there support asynchronous singular data types as first-class citizens already, right? And that's a little bit different, because if we now take a look at this, there's one box missing on the right top side, of course. And this is usually where we see streams, right? Streams are nothing else than just another data structure in plural space and asynchronous time. And they usually have a subscriber, and they usually have an emitter, right? So that's all, that's a stream. It's just another data structure. And the complexity just comes by not having, out-of-the-box support in most programming languages, or in many programming languages, many more getting streams as first-class citizen in there. And that's why we used all these libraries like Reactive X for different languages, which basically just provided us this data type into, or this data structure in the given ecosystem. So that's simple, right? The stream is easy to explain, I would assume. So let's focus on the other two things, on programming and designing. And I would like to first start with programming, because I think to understand reactive architectures, you first need to understand what reactivity is about. And it's much easier to just show on programming code than to show on a bigger scale when it comes to architecture. And again, I always come with a very simple example. If you think about this, right? You have a counter variable with the initial value of 2, and you have a doubled variable, which is counter multiplied by 2, right? So what is the result of doubled? There's no Easter egg. Yeah, exactly. It's 4, right? And this assertion works. That's that simple. But what happens now if we update the variable counter? If we set counter to 3, right? So we have here this wonderful line 4 and 5. By the way, fantastic comment, right? We update the counter for whatever reason. And now we could assume, right, that double could be 6. But we all know it isn't, right? So this test will fail. And this breaks our heart in the reactive community, because what we need to do then to get this test running again is that we need to reassign doubled and need to set double to counter multiplied by 2, and then our test will work. And that's the main criticism on the reactive community on how we build, I would say in a traditional way, things, right? We have this strong dependency, this strong relationship between counter and doubled. But it's very implicit, this relationship. It just exists in our head, right? We need to take care that we reassign doubled, and that's actually something we want to avoid. So counter and doubled should be explicitly bound. And there are great articles out there, so just look whatever you prefer, but I like the one from Paul Stovall, who explained this example very similar, and who introduced something which he tends to call a destiny operator. And the destiny operator is just this small thing here, and it's a theoretical concept, but what a destiny operator would do, it would actually bind counter to doubled, and whenever we change counter, the idea is that we have doubled now being equal to 6, and this test will work. And also, that's a theoretical example, we can do this, right? And now all comes together. We usually achieve this by introducing streams. So we could, for example, say counter is now not a variable anymore, but it's a stream with an initial value of 2. So we have here a stream, it has one value, and it's 2. And what we can then do is that we introduce a projection of the stream, which we tend to call doubled. So we take the existing stream and map it to another stream. So we kind of just derive from the existing stream another stream. And this is then our doubled stream, which would have an initial value of 4, right? So we project data from our counter stream into our doubled stream. And that's a very important sentence, because we will come back to this later on when we talk about architecture. So again, when we update the counter, we will probably just emit a new value to our counter stream. This will update the stream, and we'll add 3 to the existing stream. And in the same way, it would also directly reflect in our doubled stream by adding here a value of 6, right? And then we can basically just make an assertion, say doubled value is 6. And that's the essence of reactive programming. And that's again just a theoretical example, but if you would look at RxJS, in maybe there's some Angular developers, right? Then this would look very similar than just in this pseudocode, right? We would have a behavior subject, which is a stream with an initial value. of 2, we would have a transformation or a projection of the counter stream into the double stream, and basically we would just emit a new value to the counter stream, and then we would ask the doubled value for being 6, and this test would run through. So that's working code. You can run this, right? This is really the reality, and more modern frameworks, like for example in the JavaScript context, which was also very strong in pushing this reactive programming paradigm to the front. There's, for example, Svelte, right? And Svelte takes a very, very beautiful approach on this. You can just define a new variable, counter again, add another variable doubled, and this is counter multiplied by 2, and you see this dollar prefix in front of it, right? And this one makes in Svelte a variable reactive. So whenever counter changes, doubled will automatically change, and when we assign counter to 3, doubled will be 6, and this test in Svelte will work, right? So that's already very near to the initial concept which Paul Stoll described on his blog. And there are much, I know Svelte is already age-old in the context of JavaScript, but if you really want to see a newer concept here, take a look at, for example, Solid.js, which also has a very beautiful approach how to tackle this beast of reactive programming. And now the idea, and that's why you're here, right, is to apply these concepts of reactive programming also on architecture. That's what we often do, right? So we take, for example, CQS and apply it to architecture and call it CQS. So we often see that concepts which can be applied on software design or software engineering can also then be applied on higher contexts, like, for example, software architecture. And of course, that it still makes sense, yeah? That's what we hope for. So let's dive into microservices. As you all are familiar with microservices, I took a very simple example from kind of a project we worked on a while ago. It's in the banking domain, so I work a lot with fintechs and also traditional banks, so that's why I usually choose this domain. And let's assume we have a couple of services, right? We have a user service, this user service calls an account service, and this account service calls a ledger service, and then you have some kind of web banking UI, and this web banking UI allows you to transfer money or to make a new payment. So I can say I do a payment, 20 euros from my account to Lisa's account. And if I perform this payment, then this will trigger a request to a user service, so transfer money. The user service will trigger a request to the account service to trigger a payment, and the account service will trigger the ledger service to create a transaction. And if all went well, we get back the responses, everything is great, and the money was successfully transferred, right? Unfortunately, that's the happy path, right? That's usually not how it's working. Usually, if you work with ledger systems or ledgers in general are often quite slow, or some legacy systems, so they just don't want, they want to act like you expect them to act, and they are maybe just, you know, in high latency mode, just don't respond, and then you're running in this, you know, circle. And if you ever did this, triggered a payment, and you just saw a loading circle for quite a while, yeah. This is not a cool user experience, right? You hate the bank immediately, right? And maybe the ledger comes back at some point in time and everything works still, but still something we actually want to avoid. And we tried to solve these issues, right? We tried to solve these issues for a couple of years with retries, timeout, circuit breakers, all this stuff which we like so much because it's so cool ideas and paradigms, but actually introduced a lot of complexity, and then we needed to synchronize all this stuff, right? Because if you have different timeouts on different services, then there's a chance to DDoS your own system by you know, one service is still running in a timeout and the other one already retries and stuff like this. So lots of complexity didn't really work out for us, right? And this was kind of the first generation of microservices I saw, this synchronously integrated microservices, yeah? No blame, we did the same thing for quite a while, but we realized it's not the way how you should probably do it, right? This kind of synchronous integration. And the solution was kind of simple, right? People started to put the ledger, which is, for example, not available or not so highly available as other parts of the systems. We put queues in between to isolate these high latency services. And if you now trigger a payment, basically, what's happening is that we just send, you know, this command to user service. This user service sends it to account service. This account service puts it in a queue, and then we are done, right? Because the queue guarantees us that it will bother the ledger as long as it can. That at some point in time he will work on this event. And then we show to the user that the payment was accepted. And that's already a very simple but important differentiation here, right? We show the user that payment was accepted. It was not done. We accepted it, and we will do it somewhere in the future. So in HTTP codes, we switched from 201 to 202, which is important to understand this also from a UX perspective. And when the ledger then at some point in time is available, it picks up the message and everything hopefully works out well. But if you isolate one bottleneck in your system, you spot the next one, right? That's the idea of bottlenecks. So you put queues then maybe between the user and the account service, and then you put queues between the web banking and the user service. And this was the big times of you know, all these tools like RapidMQ, so this whole ActiveMQ and solutions like this. And this was kind of the second generation of microservices, message-driven and asynchronously integrated, already solved a lot of problems when it comes to resilience and when it comes to stability of the system or responsiveness in general. But there is anyway a big hidden elephant on this picture, right? And I did this by intention, because if you Google for microservice architectures, you often find pictures like this. And that's a main issue, right? That there's something totally fucked up in this architecture, right? And you realize this when you talk to a product owner, for example. So some product owner here? Okay, cool. So a product owner would probably tell you as a customer, I want a transaction to be booked by the ledger, right? No product owner would ever tell you this, because as a customer, I don't care where my transaction is booked, right? I don't even care if I have a transaction, right? So a customer would probably say, as a customer, I want my transaction, or I want my account service to update my balance. Again, this will not happen, right? No customer cares about this stuff. What the customer actually cares about is a very fancy feature in a bank to transfer money, right? As a customer, I want to trade money to someone else. That's what's happening. And now we have the issue, right? Because now this product owner needs to go to the user service team and say, you know what, we have this fancy new feature that we need to transfer money from here to here. Can you please change this? Can you add an endpoint? And then you probably call the account service, then it needs to go to the team who kind of builds the account service and say, hey, you know what, you have a new request from the user service coming to transfer money, and so on and so forth. And then he needs to go to the ledger team, does the same thing again and say, hey, you know, in your queue you get a new command that you should kind of book a transaction. And that's not how it's working, right? Because this doesn't allow us to, you know, independently build business features like this. And this is what we tend to call the entity service anti-pattern. And all through, we are kind of aware that this is still a big problem. I still see new teams, you know, building microservices like they would define database entities. And that's a big issue. And we understand this, I think, as an industry. There are lots of people who publish, also from the domain-driven community, to push this idea further and say, hey, we should stop doing this, right? We should not build our services based on data objects. So let's create them along customer journeys or user stories, however you tend to call these things. And again, this idea is not new. I think yesterday Uwe Friedrichsen already mentioned this fantastic paper, or one of the fantastic papers from Panos from 1972, where he already explained that we, you know, should build or structure our software based on user flows and not based on data objects. He called the things differently, but basically he meant the same thing, that we should start to create our services, or let's say to modularize our logic around customer journeys. And that's what we did, right? And as often, there's no problem in software engineering which you not can solve with another layer, right? And that's what we often ended up then. We just renamed those classical microservices domain services, right? And in front of these domain services, we build our journey services, right? And those journey services then, for example, payment. As a user, I want to trigger payment. So this payment service then needs to go to the user service, to account service, to a ledger service, probably even has an independent team to manage it. And if the product owner comes now and says, you know, we need this fancy feature finally to get a payment done, then you need to go to 4 teams, right? Didn't improve anything, did just make things worse. And even worse, people started to put this stuff into backend for frontends. And I have a long history on backend for frontends, but that's really one of the worst things we see out there, right? That we have this journey, this flow logic in backend for frontends living, And then we have a web backend for front end, we have a mobile backend for front end, and basically what we do is we duplicate our payment flow logic, and if the product owner comes again, right, it needs to go to 5 teams now, and that's just a mess. So just as a short reminder, it's not the part of this talk, but no domain logic in backend for front ends, right? This is just, part of the front end living on the backend to avoid overfetching and over requesting. So what to do? How to solve this issue? Well, it's actually very simple, right? So if you think of this payment journey, then you would probably also have a balance journey where the user can see its latest transactions, its current balance, and so on and so forth. And this balance journey would probably also need the user account and would also need the latest transactions from the ledger and so on and so forth. And we, for example, need the user account because we need the account data, right? So in many situations, we are bound because we kind of share the same kind of entity data. So we all probably need accounts, or we all probably need users. So these are typical examples which you can hardly give to some service, but which is often used by many services. And this is what I tend to call the customer journey and entity data mismatch problem, which is kind of a big issue, and you cannot really get over it, because if you think about it, then in each system you have those entities, like for example users, or like for example accounts, or like for example transactions. And on the other side, you have these customer journeys, where you basically want to build your verticalized teams around. So for example, that you can do a payment, or that you can do user onboarding to your banking application, or that you can do fraud detection on transaction batches. So for example, payment would probably need a user, right? Would probably need an account, and would probably at some point in time even need a transaction. And onboarding would probably need a user to create a new user and to create a new account for the user. So it would probably need user and account. And fraud detection would probably need accounts and transactions to see if there's something faulty going on in the system. And here you see the problem, right? We have this mismatch of entities and customer journeys. So each of them, in this very simplified example, for example, needs accounts. And that's the problem. And that's why we end up in this, whole kind of spaghetti dependencies here, where everybody then ultimately calls the account service. And if the account service goes down, we have a big issue, because all our other systems or all our customer journey services stop to work, right? So how to get rid of this problem? Well, it's very simple, right? We can just say, what? We stop doing this. We just moved data to the customer journey services. So onboarding gets users and accounts, payments gets user accounts and transactions, fraud detection gets accounts and transactions. Well, looks perfect. We have total service autonomy, but on the other hand, we have total data duplication, right? I mean, not all of those services can, for example, own the user. And then we need this data synchronization, and that's usually a very complex thing. And that's one of the key messages. If you just take one thing from this talk, and if you build microservices, or let's say any kind of distributed systems, doesn't need to be microservices, always clarify data ownership. Yeah? That's probably one of the biggest flaws we see out there, that it's not clear who owns which data, right? And we end up in these messy states where, users are duplicated, and you cannot even find out what is actually the leading system on this data. So we probably need to define who owns which data. So we could say, for example, onboarding interacts a lot with users. So usually good examples, if these services, if these bounded contexts create these data, right, then they're a good candidate for owning this data. Or if they very often manipulate or change this data. In our example, for example, we could say that the onboarding service owns the user, right? And the payment service owns accounts and transactions. And whenever, for example, the payment service now needs a user, it goes to the onboarding service and asks for user. That's not rocket science, right? That's synchronous call again. That's what we wanted to avoid in the first place, because if onboarding service is down, our payment service is also broken. And then, of course, you can say, yeah, we can add a user cache here and stuff like this. Again, we've been there. But then you have these problems of cache invalidation and all this stuff. So there must be probably a better solution, right? And now I'm coming back to this very simple example from the beginning, where I showed reactive programming in a nutshell. And I said, we project data from our counter variable back then into our doubled variable. And actually, that's the same thing we want to do here, right? We want to project users from our onboarding service into our payment service. So we have onboarding service who owns the user, and we have the payment service who needs up-to-date projection of those users in its service. So if we stick to domain-driven design terms or event storing terms, for example, we could say there's a user change command. So with the command, you change the user aggregate, and whenever the payment service, for example, calls this command or triggers this command, the aggregate will create an event, which is the user changed event. And this event then will probably update the user read model in the payment service. Yeah. And that's CQS in a nutshell, just for the sake of saying it. And what we usually do then is that we apply a stream in between, right? So we push this user changed event to some kind of stream, and basically then we transform it and we apply it on the user read model. And there's this TTK. People who know me well always ask for the TTK in my talks, the time to Kafka, because I'm kind of known as a fan of Kafka. But it's not the only thing you can use for the streams, right? You can use Kafka, you can use Pulsar, you can use KubeMQ if you're a Kubernetes native. You can even use a Redis. It doesn't really matter in this talk now what we use here, but in the end of the day, we need some kind of streaming system which helps us to achieve this. And in our example, we would, for example, say if the onboarding service changes the user, we publish an event to the stream, and this event will then basically be consumed by the payment service, and whenever the user changes or a new user is created, we take this and consume it there, right? And if another user is created, we get another event, and basically we consume it, and what we do is we put in a projection, and that's some kind of fancy term for a read model. So we hydrate changes from users into our projection, which is kind of just a reading persistence, or must not even be a persistence, a reading state of users in the context of payments. And if the user changes again, we do this again, and we basically just update the projection. And we can do this, of course, for many more things, like, for example, transactions. Whenever a new transaction is created, we publish this event to Kafka, or here you have it, to your stream, and then basically you just update your transaction projection in your fraud detection, right? So these projections actually allow us a great thing. They allow us to have independence of those services. So if the onboarding service is now down, we probably don't need it from the payments perspective to fetch the users, because we have the users already. We have the users projected into our system, and if the onboarding service comes back again, it will update this projection again. But we are kind of not bound on runtime level that much anymore when a user requests data, and that's basically what we did. I will talk a lot about this a little bit more in detail later on. But when I explain this, then usually people ask, but didn't we just not introduce eventual consistency, right? Everybody seems to be super afraid, and I can understand, of eventual consistency. It's our baddest enemy in distributed systems, obviously. And it's really hard for me to answer this question, because many people understand many different things when it comes to eventual consistency. And I, for myself, usually split it up in different phases of eventual consistency. And we could do a whole talk. I guess we could even do a whole workshop on eventual consistency. But for now, let's keep it short. But what I usually say is that we have something which we call eventual divergence. So think of an event. The user changed the age from 20 to 21, and the user changed the age again from 21 to 22. And then we have two services which are interested in user age. So we have a dashboard service that consumes user changed event, and we have a profile service who consumes the same thing. So dashboard service starts to consume, gets user changed event, gets user changed event number 2, and has a user with age of 22, right? Straightforward. Maybe the profile service gets it in a different order, right? So it uses the user changed event, gets the user changed event with the age of 22, and then gets the user changed event with the age of 21, and then we have a user with an age of 21 on the profile service. So we have a divergence here, and this is something we usually can easily overcome, right? Most or many of our beloved streaming platforms allow us, at least on partition level, ordering guarantees. Or we can, for example, use idempotency if we know, okay, there was already a new event coming, we just throw out or just remove the older event by working with timestamps or something like this. So probably something we could easily overcome. The second one is eventual variance, where we have a stream. Again, we have a ledger system, for example. Ledger system pushes whenever a new transaction event was triggered to our stream. But maybe, and that's really possible, Sometimes people forget this. Our stream is not available, or at least the connection to our stream is broken. Then the ledger system needs to retry publishing those transaction event again. And maybe he tries one time too often, and the event lands there 2 times, right? And then if a dashboard service consumes this event, it shows the user balance of 20, which of course problematic. But again, we can overcome these problems of eventual variance usually by deduplication, quite, I wouldn't say easy. Nothing of this is easy, but there are solutions to solve this issue. I think what most people fear when we talk about eventual consistency is not divergence and variance, it's eventual latency. Right? So where we have this user changed event again, we have a dashboard service who consumed this, and we have a profile service who consumed this, and then we have a user changed event of an age of 22. So the profile service consumes it, update the user to age 22, and then for whatever reason we again have a broken network between dashboard or stream, or dashboard service in general is broken. Nevertheless, we cannot consume this new event, and our user stays his age of 21 in the dashboard service. And then the user comes, goes to the dashboard, says, oh, I'm 21 years old, that's great. Goes to the profile, says, oh shit, I'm really 22 already. The system is broken, it doesn't show me the same thing on 2 different pages. And that's, again, a very complex problem. The simple advice I usually give is this is a problem usually bound to a single user context. And what I mean by this is that this is a problem you can often come on the UI level of things. Because this is usually problematic for one single user, right? So if a single user goes to dashboard and profile and doesn't see the same age there, then it's problematic. But if user A sees the age of 21 for user C and user B sees the age of 22 for user C, then that's usually not such a big thing, right? Because people are usually not sitting on the same table doing this stuff, and you know, it's just a little bit a latency which the other user currently sees in having the latest user age. And that's important because then we can work a lot with optimistic UIs, and we can do a lot with, you know, solving this problem on the UI level, because it's actually also not only a single user context, but it's usually also a single user device problem. So usually it's not even a problem if you have, you know, age of 21 on your laptop and you have a age of 21 or 22 on your mobile device, because this is where you just updated it. So this latency problem really needs to be understood in detail, but in many situations, optimistic UIs, for example, are an option to solve this. Yeah? So we have those 3, right? We have eventual divergence with same events, different results. We have eventual variance, same events, different quantity of those events, and we have eventual latency, same events, different realization. Again, problems are overcomable. We can, for example, do ordering guarantees. We can have at least once delivery for variants and deduplication mechanisms. And we, for example, can work with optimistic UIs to kind of solve this latency issue, at least for the user. So the important part, the too long don't read, is eventual consistency is often used as a knockout argument for, you know, this kind of arguments, but in most situations, if you really go in detail and need to understand this and sit together with business, it's not, right? In most cases, it's not a knockout argument, and usually if you think about it in detail and understand the trade-offs, there are solutions to go with kind of a good middle way, which fulfills also the user needs. So, coming back to our system now with these beautiful projections which are hydrated based on events on a stream, we have now this service autonomy, which is of course beautiful. And I give you a real world example now. So as I mentioned, I work a lot in banking, and especially in 2014-15, you know, when all these neobanks started, lots of banks started to rethink the strategy, wanted to invest a lot in mobile banking because they also wanted to have cool banking applications like N26 or Revolut. And it was cool because this was a project, one of the first ones back then, where we really did good user research up front, right? We just didn't start programming, we really took a look, what are we actually doing, why are we doing this? And there were really interesting numbers. These numbers are interesting for many perspectives, but there was a research what the people actually doing in mobile banking. And it turns out that 93% of users are basically, you know, just checking the latest transaction, the current balance, right? 3% are tracking a payment and 4% are doing something else. 4% of all operations by users are something else, like, I don't know, lock your card, right? I think from an agile perspective, that's wonderful, right? Because if you talk to people who work on mobile banking, and probably if you talk to me back then, I invested most of my time in, this fancy feature to lock your card, right? Which is super complex because you need to call 15 systems, but nobody ever uses it, right? It would be much more efficient to focus on, showing the user his current money and show him, I don't know, the latest 20 transactions. And this would fulfill 93% of what the user actually expects from this mobile banking application. And if we take a look at our architecture, we could say, user triggers a transaction. This transaction event, of course, all very simplified. Yeah, I should add this to every slide. All this is simplified. Yeah, in reality, it's much more complex, but it should give you the message, right? And then this transaction event is pushed to a stream. We consume it somewhere, put it in our projection, store it there. And when we now ask for latest transactions, we just go to our projection here. That's so important to understand this. We don't need to go over here, right? We just go here. That's a very, my drawing skills are not perfect, but that's very important to understand, right? So we have this high isolation of systems. And if you then, for example, for whatever reason, your onboarding service doesn't work, right? Or your payment service doesn't work, or your whole system burns down actually, right? Users can still look at their transactions and at the current balance, right? So 93% of your users can actually achieve what they want to achieve, and that's fantastic, right? If we understand those non-functional requirements, like this one, then we can build architecture that allows us to achieve this, right? And for example, if a lot of users want to see their current transactions, we can easily scale this up. We can say, we build up a second overview service, hydrate your transaction, and basically, very simply, horizontally scale those architectures. So if one service goes down, the other one can basically take over. And another thing, if you think about triggering a transaction or triggering a payment, if I go to my web banking from Lisa and transfer from Lisa 10 years to my, or 20 years to my account, then I just publish, this event from a payment service to a stream, take it over there, put it in projection, and maybe just push it through to the web banking application. And then I don't need to do any refreshing or stuff like this. It just appears there, right? It appears there, updates my balance without F5ing the web page. And this is, for example, we use a lot of GraphQL these days, right? Because GraphQL has lots of good attributes, but the best one, and often the most underestimated one, is that it, define subscriptions as first-class citizen. It's really basically the same thing like a query, you just put a different keyword there. And if you really go into this direction, and if you want to really make it beautiful there, then at least for me, very beautiful or always very appealing is, then you know that you go into the wrong direction if you, for example, on GraphQL just work with mutations and subscriptions and don't need queries at all, because then you're full end-to-end reactive, which makes a lot of sense, makes a lot of fun. So we have great capabilities for real-time synchronization in the system, so we don't need to design this afterwards. So if we already know up front that this is something which is important for us, then reactive systems are very handy. Another thing, for example, is working with legacy systems. We all know legacy systems are hard. It's really tough to get rid of them, to kind of decompose them into more modern systems. But even if legacy systems are hard, usually what's much harder is to decompose the data, right? So legacy databases are even worse. Yeah? And there's a fantastic tool, at least in my tool belt when I work with decomposing monoliths, is to, for example, take out the users by using change data capture, and whenever, on this Oracle legacy DB a user changes, we publish an event to Kafka Connect and to Kafka, and then we consume it, and basically we have the users then available without needing to go to the legacy system all the time, right? Because we just have it there. And that's kind of the third generation of microservices to build them on reactive data streams, and I'm nearly done, yeah? And the cool thing is that we have a lot of fantastic attributes there. We have high resilience, we have horizontal scaling, and we have real-time integration, and we have good integration with legacy systems. But that's not the end of the story, right? We could even go a step further. And that's interesting now, because if we think about the dimensions of scaling, which we usually talk about, then we think of two of them, right? We have vertical scaling and we have horizontal scaling. So we take a service, scale it up, putting more memory, putting more CPU, putting more space into it. That's something we actually want to avoid because it's very cost efficient in cloud native infrastructures. And that's why you, for example, go more into this idea of horizontal scaling. And as I showed you before, we could now say, you know, each of these horizontally scaled systems get its own projection, gets its own read model. This sounds good in theory, but it's very unpractical in reality because each of them must consume all the events from the stream. This takes a lot of time in starting up those services. You probably need to be fully event sourced to really always rebuild these projections on every service instance start. So we will probably go with something more central. So we probably have a single database for all instances of this service, so that we, you know, just keep this database, and whenever a new instance is coming up, it takes this existing database. But that's problematic because at some point in time we are not able to scale anymore because our scaling limitation is the database which all instances of this service are using. And that's why it's always important to understand that there's a third dimension of scaling, which is something which we tend to call sharding. And we could, for example, shard those services. We could say, you know, we split up those services based on user groups. So users from a specific group go into those services and users from other groups go into other services. We could, for example, do this by countries. Users from Austria go to service instance 1, users from Great Britain go to service instance 2, users from Hungary go to service instance 3. And basically then we can easily build up projections for each of these instances because we just need to consume those events which we are interested in because we know exactly which users will come to our service and we'll just consume the events from Hungarian users. And we can even horizontally scale this stuff, right? So we can do sharded horizontal scaled architectures if we really need it, right? Yeah, I'm nearly done, yeah, sorry. And there's this user-triggered payment event, right, for example, which we just saw. We maybe see this is coming from a guy from Great Britain, and that's why we put it into our partition 1, which is our shard for British users, right? And then we just, you know, go through this whole kind of service architecture, go to the payment service for this specific shard, so the second instance, take it, put it to another stream, and so on and so forth. And then basically we end up somewhere in the shard of the ledger, where we have it in the Great Britain ledger shard for transactions. And so we have very independent shards, and this actually allows us, as I mentioned before, to build up independent localized projections for each of those shards, which makes the system very easy to scale because our projections are much faster to spin up in the beginning. And this is, for example, where I use Apache Flink or Apache Kafka Streams to achieve this. And you can even go further, put this all into kind of a sharded data sync like Elasticsearch, and then, you know, deploy sharded UIs for each of those countries, and, you know, have kind of fully independent sharded systems, and you can push millions of events through the systems, right? We did this, and this is actually an architecture which independently nearly scales, right? You cannot really, I mean, you can, I'm sure you can, but it's really hard to kill this. So we have near independent or unlimited scale when we go with sharded stream-based architectures. And that's kind of the last generation of microservices we see, right? So fully sharded and fully stream-based, and this gives us massive throughput, this gives us extreme scalability, and that's of course fantastic if we need it. So let's sum up. I showed you a couple of different generations of microservices. I didn't mention monoliths for bad reasons, because I like monoliths. You should also like monoliths. Everybody should like monoliths. And it's important that you stick to the monolith as long as you can. And once you have the feeling, this monolith is getting too big, we're stepping on each other's feet, think about first going to a modulith, right? That's the new fancy term we found out. And basically, if this is still not working, before going synchronously integrated, don't do this, yeah? It's just pain. Just stick with the monolith, as I mentioned, right? And if you really at some point in time need multiple deployment units because we want to have independent deployments, then think about going asynchronously integrated microservice, which I showed you beginning with these events, RabbitMQ, whatever you have, right? And at some point in time, you will find out that if you want to share data between those services, you anyway need to switch this over, right? You need to go from this pull-based system where I ask another service for users to these push-based systems. And this is actually where we land in the land of reactivity, right? Where we switch over to push-based systems from pull-based systems and can easily achieve this. And if you even need more throughput, then go with what I showed you in the end, sharded systems, where we can easily do this by stream-based architectures, easily. So we have massive throughput. And that's basically the thing. And as always, as James Lewis always says, this comes with cost, right? So you get a lot of features with these architectures from left-hand side to right-hand side. The more you go to the right-hand side, the more fancy features you get, but the more costs you pay, and the costs in architecture we pay are always the same ones, and this is basically complexity. So start left, stay as long as possible on the left, and really just, if you need, go as far as to the right as you really need. Yeah? You don't need to build stream-based systems in 95% of the use cases. And that's it. Cool. This was the rise of reactive microservice. Hope this was useful. Thanks a lot. Sorry.
It was an amazing speech. It was very interesting. Maybe only one question, please, the most popular. Remind the people that maybe they can catch you up after it.
I'm here till my train in the evening. Yeah.
So
cool.
How is this stream-based read-only data projection any different from using a replicated slave database?
That's a very good question, actually. That's a very good question, because I see that many teams out there are actually not utilizing those features of Aurora DB, where you can actually do this, right? Where you can build read nodes from your Aurora, Postgres, MariaDB instances, and you don't need to go this whole way around Kafka and stuff like this. So that's something you can definitely do, yeah? If you have a database which supports you, that on a user service you have the write node of your Aurora instance, for example, and on the other services who just read this user data, you just have the read nodes. Go for it, yeah? Stick to the stuff the cloud providers or modern systems give you. I don't say that this always needs to be kind of this, fancy-fashioned way with streams and consuming to streams. So in many situations, this is probably a good fit because it's less complex. But in some more detailed situations, it would probably still make sense to go with this, event approach, because sometimes these events are important, right? It's not just sharing the data, but it's reacting to those events, right? And if you just, have write and read nodes, and you just duplicate the read nodes, then you never really get explicitly the knowledge that something happened. You just get the data. And if this is enough, it's good enough. If this is not enough, you probably still need events.
David, we have something for you. In the name of all the Craft organizer. Thank you, David, for your wonderful talk at Craft. And please help me, people, with a really nice applause to David.